Hello. Good afternoon, everyone. Okay, so today we will have the special seminar by Dr. Pei-chen. So I will invite Dr. Pei-chen on stage soon.
Hello.
Hello.
Can you hear me?
Yeah, I can hear you clearly. Okay, so probably we wait for a few.
Try to figure out how to share my screen. Am I hearing Ling Ling?
Yes. She's just here beside me. Let me invite you on stage again, and then you can practice how to share the slide.
Start sharing screen. Okay, it's asking me about that. The window. Okay, I think this is the one. Okay, can you see the screen? It looks dark to me. Let's change sharing window. Is my screen on? Can you see my screen? Yeah, I think you are muted.
Your screen and see your cursor moving around.
Okay.
Should be okay.
Okay, great. So yeah, just let me know whenever I should start.
A few more minutes, and then we will proceed with the presentation.
Okay, sure.
Actually, today we have two talks. So one talk is at 3 p.m. and another talk is your talk at 4 p.m. So there will be people from the first session would like to attend as well. As well as Professor Surathep, who is the so right now I'm the alternative host. The hotel session.
Okay.
So probably a few more minutes I will let you know. So first I will give introduction about you, and then we will follow by your presentation. Time, so probably let's start. So first, let me today it's our honor to have Professor Pei-chen Su to join our seminar, like our webinar today. So I would like to give a brief introduction of Professor Pei-chen Su. Okay, so Associate Professor Pei-chen Su is currently a faculty member in School of Mechanical and Aerospace Engineering, Nanyang Technological University, Singapore. She is also the Cluster Director of Multi-Energy System and Grid Energy Research Institute at NTU, and her research interests are in applying microsystem technologies, nanoscale thin film, materials engineering, and nano-patterning technologies at the interface of energy conversion device. Specifically for fuel cells, she is pioneer in development of high power density nano-thin film oxide fuel cells at low operating temperature and keep reading cells performance in the literature. Her research interests include low temperature solid oxide fuel cells, micro-nano fabrication, nanoionics, and thin film energy materials. Her research group focuses on developing new electrode and electrolyte materials and nano-engineering of cell components via thin film deposition technologies, design and fabrication of scalable micro solid oxide fuel cells, and study of reaction kinetics between cathode and nano-thin film electrolyte interface, all together with an ultimate goal of commercializing a practical device for solid oxide fuel cells below 500 degrees Celsius. So please welcome Professor Pei-chen Su. We are looking forward to your talk.
Okay, thank you very much for the nice introduction. Okay, so today I will be sharing a work that's about solid oxide electrolyzer electrode, which is a rather new area that I just started to work on a few years ago. Okay, so because these years in Singapore, hydrogen is getting very, very important, and the government and a lot of agencies, funding agencies, they are paving the way to welcome a hydrogen economy. And so in Singapore, the energy, research area, when it comes to fuel cell, it wasn't really so, so popular because it used to be very, a lot of money is being invested to fuel cell, but as the outcome is not as expected. But these years, because of the hydrogen economy, that's drive this entire need. So now we are coming back to work on solid oxide fuel cell electrolyzers, etc. So so I spend more time on solid oxide fuel cells actually, but electrolyzer cell, this topic is actually kind of started by one of my PhD students, who is a very brilliant student, graduate from Chulalongkorn University in the Department of Chemistry. So he has been doing PhD with me for a few years. So this is the work that he has conducted. So today I will introduce this piece of work, which we study the electrochemical performance of this barium doped SFMO oxide as the fuel electrode for solid oxide electrolyzer cells. Okay, so the title says moisture dependent because mainly we are trying to understand how is this barium doped SFMO behaving under the changing moisture contents. Okay, so this is the basic schematic of a solid oxide electrolyzer cell. So for those who are familiar with the working principle of a solid oxide fuel cell, SOEC is a reverse operation of solid oxide fuel cells. Okay, and when it comes to research, a lot of people are more focusing on this cathode, or it's more often referred as a fuel electrode, because there's a lot of things going on this fuel electrode. There's a very complex reactions, including this water reduction reaction, and also there's hydrogen generation here. So it's very busy, and therefore its performance is quite of significant interest. So what we are looking at is here this few electrode and all the performance here. So, the material of selection is based on the SFMO, strontium iron molybdenum oxide, and it has a double peroxide structure. And its key, advantage is that, it's very stable in both oxidizing and reducing Adams fields. So now the most common electrode for solid oxide electrolyzer is still the nickel FYZ, but it's not the most stable material in this environment. So SFMO have such advantage, and it also has very good catalytic activity for electrolysis of water or for carbon dioxide. And also it has good electrical conductivity. So it's quite suitable as an electrode. Okay, so there are some work that has, studied about, SFMO in the SOEC, okay, and either as a fuel or air electrode. So yeah, in this table, we find, these are the three are working on a fuel electrode, and one is on the air electrode, and at about 700 to 900 degrees centigrade. Okay, and there is, fuel in terms of water, CO2, or, co-electrolysis. Okay, and the performance are quite decent. Okay, so this gives people some confidence that, this SFMO indeed have is promising as a SOC electrode. So, okay, so what we are thinking of doing is trying to see if we can make it even better by doping its A site. Okay, so the A site is a strontium, and if we replace the strontium, some part of it, by doping with a barium, okay, then we can induce some lattice expansion. So this barium is larger than the strontium. So this larger A site cation will expand the unit cell. So it's likely that it can facilitate the oxide diffusion, within the electrode, and also improve the electrolysis performance. So that's the idea. Okay, and in terms of the selection of this A site dopant, we choose barium because it has a bigger ionic radius than the strontium, but it's not too much bigger. So that could facilitate the smooth doping in this SFMO. And there are some studies before also show that 0.2 of dopant is appropriate composition for the lowest polarization resistance and also the best electrical conductivity. So we just start with a 0.02. And in fact, we try to survey a different composition, but this 0.2 still give us the most stable kind of phase. Yeah, so we choose this. We stay with this 0.2. Okay, and then it's never been used in the electrolysis of water before. Okay, SFMO has been studied, but the barium doping is not really been looked at yet. Okay, so we look at it. So the objective of this work is that we try to evaluate whether the barium doped SFMO will be a suitable fuel electrode for SOEC, in terms of water electrolysis. Okay, so again, we look at this fuel electrode and its performance. So, to do this experiment, we build a half cell, and then we try to see, under the presence of hydrogen and with increasing water contents, how is this electrode performing? Okay, so this is the electrode we are looking at. So come to the experimental. So this is the preparation of our electrode material. So we make our powder with the solution combustion synthesis. Okay, so we mix all the precursor together, and then the solution in DI water, adjust the pH value, and get the metal solution, and then heat to generate the ashes. And then we calcinated it at 1000, 1100, 1200 degrees C for 5 hours. Okay, and then finally we obtain this BSFMO powder. Okay, we also make the SFMO powder for reference just to compare whether it get the right phase. So we first check the X-ray XRD to see whether we get the right crystallinity under this different calcination temperature. Here is the X-ray diffraction pattern for B2 SFMO. Okay, so we calcinated at these 3 temperatures, and then with a reference to the SFMO and calcinated at 1100 degrees C. And you can see that for B SFMO calcinated at 1000 degrees C and 1200 degrees C, there is some impurity phase that's visible, while for the calcination at 1100 degrees C, the XRD looks very clear. Okay, so there is no impurity phase being spotted. Okay, and also the pattern is almost the same as the SFMO. Okay, so we look at this around 32 degree of a peak, and we can see that there is a clear shift of this peak, and then it's slightly away from its original position, meaning that our barium, because of it's a slightly bigger or radii, that it's successfully incorporated into the A site. So we go ahead and make our half cell for evaluation of the electrode. Okay, so we have a SDC as an interlayer. So we use a YZ as the electrolyte and put a SDC interlayer, and then we go through all the process to put the electrode. We use a screen printing to put our B2 SFMO electrode on it, and then we also put the calcinated. And then we also put the platinum current collector on top of the B2 SFMO, and also the platinum on as a counter electrode, and also the ring reference electrodes, so made by platinum. And then we go ahead and and characterize it. So we first look at the powder of the B2 SFMO calcinated at 1100 degrees C. And the particle size is about 500 nanometer, and you can see that it's rather uniform. Okay, and this is a cross-sectional view of the half cell, after the final calcination at 800 degrees C. And it looks okay, and then we didn't see any delamination between the layers, which is a good sign for the integrity of the whole cells. Okay, so again, we try to understand how this BSFMO is electrochemical performance, and with a steam content at the fuel electrode. So again, we purge hydrogen, and together with the increasing water steam contents from 3%, 10%, and all the way to 60%, to see how this B2 SFMO electrode is taking this moisture content and the performance. Okay, so we perform the test, including the electrochemical impedance spectroscopy at under SOFC mode with 2 different voltages at OCV, and also under SOEC mode. Okay, and then we extract the from the EIS result to do the DRT, and to identify which process is most affected by the changing moisture content. And we also check the polarization curve, the IV curve, to see the overall performance. Okay, so this is the first result, the EIS and DRT plot under the SOFC mode at the 0.4 volt. Okay, so you can see that this the black one is the 3% water content, steam content, which is the lowest. And then as it continues to increase the moisture content, the impedance continues to increase. Okay, so and we go to look at the DRT plot, which shows 3 distinctive characteristic peaks. So the first peak is a low frequency, which is account for the surface absorption, desorption of hydrogen or gas or water vapor. So this will be the main peak that we look at, because we are changing the steam contents, on over the electrode. So this will be the most affected reaction by the changing moisture contents. Okay, and there are another 2 peaks, which is the intermediate frequency peak for oxide transport within the electrode, and also the high frequency for charge transfer process. So again, we look at this low frequency surface reaction peak. and we can see that, it's increasing. So meaning that this increasing in this impedance are, from this surface reactions. Okay, so why is it increasing? This can be explained because this is under SOFC mode, and then the hydrogen and the vapor coexist. So when we increase the water vapor contents, the hydrogen is being diluted, and therefore that causes this increase in the polarization resistance on the surface of the electrode. Okay, now let's look at the OCV. So this is the OCV for the EIS and DRT plot. So we can see that, again, 3% is the lowest and increase all the way to 60%. And we can see that the impedance is rather stable, with all moisture contents. And we look at the DRT plot. So again, for the first peak, we can see that this first peak, when it's black, which is the lowest moisture contents, is a bit higher. And then when it goes to the red, which is 10%, slightly increase of moisture contents, it dropped. And then, it start to increase again. So it goes through a drop in the peak one and then increase. Okay, so that tells us that, there is probably, we guess, we think there is a activation process that when the moisture content is too low at OCV, then the electrode is not fully activated. But when the moisture contents get to 10% and it start to kick in, and so the reaction start to take place. Okay, so likely it's due to the surface activation at 10% of steam content that start to kickstart the electrode reaction. Okay, now let's look at the the most of the concerned result, the SOEC result. Okay, we can see that when the moisture content 3%, this black one, when it's still very low, it's expected that this impedance is very high because there is not enough water for the electrolysis. And as the moisture content increased 10%, 20%, and the impedance dropped very significantly. And finally, when the water content is much higher, and it doesn't really change too much. Again, we look at this DRT plot. Okay, we see the first peak. So again, this black curve, the lowest moisture content, 3% is high. And it dropped to 10% when it becomes 10% and slightly increased around this purple, hot pink, which is 20%. Then it increased again. So it also went through a drop and increased kind of, behavior. Okay, so we feel that there will be a kind of more optimized or more suitable amount of water contents around 20 to 30% that will exist. Okay, so meaning that if you have too much water content, it doesn't really take up by the electrode. Too less, they also cause the impedance high. Okay, so we go ahead and plot all these together. So for OCV, SOFC mode, and SOEC mode. So these are the values extracted for the different water contents. Okay, so we look at the OCV again. So the OCV, this black blue curve, that you can see that it drops slightly from 3% to 10%, and it remains rather constant. And in SOFC mode, the water content increased and the impedance also increased, again because of the dilution of the water hydrogen contents by the increasing moisture. And for the SOEC, this red and pink curve, it stays high in the beginning, and then after 20-30% it starts to stabilize. Okay, meaning that more moisture does not really being taken up by the electrode. Okay, and another important message here is that when you use SFMO in SOFC mode and SOEC mode, the impedance is lower under the SEC mode, which implies that perhaps this material is more suitable to operate under SOEC mode than the SOFC mode. Okay, so this is the IV curve, the polarization curves. So, this is for all the moisture contents. Okay, so, and this is applied bias. So it's probably a bit hard to differentiate. So we just extract the values at 0.4, 0.2, and minus 0.2, minus 0.4. So meaning that 2.4 SOFC and 2.4 SOEC. And then we see how the current density is changing with moisture contents. Okay, so again, for SFC, as the steam content increase, the current density drop, gradually. So again, this proves that, it indeed have something to do with the dilution with the hydrogen content by the steam. And for SOEC, it also follow, the same trend with our DRT, our EIS result, that it's dropping, when it's high. So the current density, drops with the increase in moisture content and stabilize, and then slightly increase. Okay, so this is the polarization curves. Okay, so it's this kind of optimize the current density for SOEC, again between like around 20 to 30%. Okay, so it comes to our conclusion. So by doping barium in the SFMO, we have shown that the barium can successfully incorporate into the SFMO lattice. And then the moisture response of a B2 SFMO field electrode is affecting the surface absorption. Okay, so that's been seen very clearly. And then under the SOFC mode, the impedance increased with moisture content due to the dilution of hydrogen fuel. And under the SOEC mode, the impedance decreased and becomes stable after 20% of moisture contents. Again, because due to the likely the amount of surface vacancy or defect that can take up a certain amount of moisture. So if you increase further, that doesn't really help to improve its performance. Okay, so between SOFC and SOFC mode, we found that the B2 SFMO is like the most suitable for the application for SOEC. Okay, so this will conclude my short talk. And in the end, I want to thank my PhD student, Kitiwa Kanglunswa, who is a very brilliant student introduced by Professor Yi to study a PhD with me. So he is very, very good. Okay, so he is under the scholarship of IGS under the Energy Research Institute in NTU. And also I want to thank the financial support for the Ministry of Education from Singapore government. Okay, thank you very much.
Okay, thank you very much for your talk. Okay, so the forum is now open for questions. So the audience, please feel free to write down in the chat, or you can, let me see whether I can invite on stage in case anyone can. Yeah, you can type in the chat and then I can invite you on stage, or you can either type in and then I can ask the question. Sorry.
Looks like Ling has some questions to ask.
Probably. She has been listening to your talk. Okay, probably in the meantime. And okay. How can we obtain the DRT equation? So that's the first question.
Okay, so I think you will need to extract from your impedance data, right? Let's see. Oh, actually, I can do this. Yeah, I think you will need to, get the data from your EIS measurement and then try to extract, the information from there to construct the DRT. Is that what you're asking?
Other question on that? This one is to Kun Nopakun. So do you need any more information?
Yeah, there are a lot of paper that you can refer to how to extract the DRT.
Okay, it's actually.
And before you do a DRT, the more frequent thing we do is we just look at the body plot, because usually on the body plot, you would already be able to see those characteristic peaks. Just if you do the DRT, I think it's more accurate, and you are able to identify the process more accurately. But the first thing to look at is your body plot. That's what we usually do.
So I just wonder whether you already compared the result with the undoped.
I think we did, but not very comprehensively. Because we mainly only focus on changing the water contents, and the undoped one we just run through it, but we didn't really compare all the water contents together with the P2 SFMO, which I asked Kitiwa to do it, but I think he's not too keen on that. He's more interested in finding how his doped electrode is working. Yeah, but I think that's a meaningful thing to do. And now we are actually working on the potassium doping. Yeah, he is a very kind of he likes to modify materials a lot. Yeah. And he likes to work on oxide a lot. So SFMO, since he joined, he proposed this material, and since day one he keep working on this material. Yeah, he's very persistent on this one.
We got another question. So can you comment if the dope cation has a smaller size than strontium?
Yeah, we haven't really thought about choosing anything that's smaller, because usually, as far as I understand, because you try to generate some space for your ion to conduct, right? So usually, what we would think, it would be try to expand the lattice and create some space for the dopant to not dopant, for the oxide ion to move around. So that's the rationale behind. I don't know what will happen if we have a smaller dopant. But now, as I mentioned, we are working on potassium. Potassium is a different kind of aspect, because it will induce charge imbalance. Okay, so what effect we are going to see, we don't know yet. We are still seeing that. Yeah.
Do you have plan to change from like water to other solvents in the future?
So when do you mean in the combustion process, or you mean in the electrolysis?
I mean moisture is solvent. In the
Oh, you mean in the test? Yeah, we did some electrolysis and co-electrolysis with the CO2 only, and water and CO2, and it shows some very funny behavior. Yeah, so but it's only on SFMO, so we are still trying to figure out what we are seeing. Yeah, it's very funny. The curve, it just doesn't look normal. It looks to me there is some side reaction that is happening. Yeah. So yeah, ultimately, because for electrolysis, you want to in a way generate hydrogen, but also you want to reduce the CO2 content. So electrolysis of CO2 or co-electrolysis of CO2 and water is what we are
the next question is, what is the difference between half cell and full cell for the electrochemical test?
Okay, so if you have a half cell, you can, I think, you can see that reaction, that particular reaction more clear without being affected by the other electrode. So, and for simplicity, and honestly, we tried the full cell to start with, but, we cannot explain what we see. So, I suggest him, why don't you just look at the half cell first, and then just to characterize the material itself first and see how it's behaving. And then you go and mess with another full cell. And then, it's easier to see, the behavior of the electrode. It's very complicated, I would say, with especially when CO2 comes in, we really don't know in the field.
But you also test separately at first, right, and then combine.
A long way to usually, okay, so Eli is very ambitious, so he always just jump for the full cell. But and then a lot of things he cannot explain. So so we always have to take a step back. Yeah, so it's usually a half cell and then symmetric cell. But for the SFMO, we usually just do the symmetric cell, because we do want both electrode to be SFMO, so that ideally, if that really happen, you can have a reverse cell. It can operate as a SOFC and also SOEC.
So audience, if you have more questions, you can feel free to type in the chat. So in the meantime, I just wonder whether, so for this material, is it only oxide conductor or is it also proton conductor?
Well, that part we don't know. We think it might conduct proton.
It might be a bit difficult.
But we don't
just
really
wonder, because it's kind of sensitive to moisture content
yes.
as well. I mean, there might be some effect from protons. It will be very interesting.
Yeah. Yeah.
I think one way to go might be
idea, then
test with tracer. Tracer. Use the tracer. Proton tracer.
Say again?
Tracer diffusion. I mean.
Tracer.
And then use the.
Oh. Okay. Actually, so the SFMO, actually we start with a proton conducting electrolyte. So initially, very, very beginning, we want to do a proton SOEC.
Understand.
But again, there's a lot more other challenges. Again, we spent a lot of time trying to make a good quality electrolyte. It's very, very difficult. Yeah. And later we work with another university, and they can sinter very nice BZCY. Yeah, that's the electrolyte we
interaction
use,
between.
Still, we couldn't get any meaningful result. Don't know why yet.
It's more stable with YSC.
Possible. It just looked very bad. Yeah. So anyway, again, we take a step.
But this YSC is not thin film yet, right?
On the simpler system.
It's more like commercial, right? Is it? Oh, more like, I see. More like pellet.
We make it ourselves. Yeah, pellet. Yeah. So the next step, which Kitiwa will work on, is to make SFMO thin film, and we probably will try to make it in a thin film SOFC or SOEC and see how. But now we try to resolve it as a as a pellet, or in the screen printing, this kind of powder process first, because it's already a lot of things that we don't know how to explain. So yeah, so again, we try to understand it more in a simple system first. When it becomes thin film, then maybe there's a lot more things that going on.
Very difficult.
Yeah, even just a platinum YZ, and it becomes thin film, and it's very, very messy. A lot of time you don't really.
I see.
Sometimes it performs really, really well, but sometimes it's bad, and it's hard to make it very consistent. So when it's good, I'm very good, very happy. But why?
Another question.
And next time,
any way or method that you may propose to modify for better work of this research? probably like future work, how to modify the your system, the material system.
Okay, so as I mentioned that we are now also working on potassium doped SFMO, and we are also working on SFMO, so these are two separate directions. One is that we keep explore how we can make SFMO better by doping now barium, and we now also do the potassium. And on the other hand, we want to, go for more practical application. So just use SFMO and try to make it work in a real SOEC. So what we do is now, because the SFMO, maybe that's another talk in the future I talk about. So when we use SFMO in LSGM and try to do the electrolysis, it's very, very strange. It's very unstable. So, we need to composite electrode, which is what a lot of people do, composite it with GDC, with SDC, and there's some other material we are trying to try now to stabilize the SFMO, especially in water, okay, no problem. But in the CO2, it's just very strange and very unstable. And, some possibility is maybe Strontium segregation on the surface, or, there's a surface carbonate forming. We don't know. So we are still, studying. So yeah, this is a material that, Kiriwa introduced in the beginning. I think, oh, very good. But turns out there's a lot of work that can be done, in terms of exploring new material and also how to use SFMO only, no doping, and make it very stable and really show it's a good stability in the real SOEC.
I think that, the audience, thank you for your patience. Okay, so I just wonder, for Singapore project work, they emphasize on hydrogen production right now, but it's not much investment on fuel cells. Or just wonder then why they want hydrogen production. It will be for fuel cell or for some other application. So what's the plan of the Singapore government on using the hydrogen?
Okay, you mean how are we going to use hydrogen? Is it? Okay, so the first thing will definitely, for transportation, right? And yeah, so for example, like buses, taxi, because Singapore is very small, and so it makes a lot of sense if you use public transportation and also trucks, and it's running on hydrogen. It's not only about saving how can I say, reduce the carbon, but also because Singapore, it has to position itself, so that it will have some economic value regionally. So, it's trying to position itself that it's like an energy kind of hub. So, for example, like Singapore will soon have a LNG, line, and will be a LNG trading hub in this region. Okay, and so how can itself, bring it forward to the next phase, that when everybody is relying so much on hydrogen, what kind of role is playing, right? So, in that sense, hydrogen production and how you can use hydrogen and how you can, expand your hydrogen kind of utilization and also trading among the neighboring country is very important. So even though we are small, but it's not like we sit there and wait for things to happen. But yeah. So how can I say? So for hydrogen utilization, what I know is about the transportation. That's a very direct thing to use. And other ideas include because now Singapore, our electricity power plant is running on natural gas, so it's already quite clean and efficient. And there are some other idea that we are trying to see whether we can add hydrogen into the natural gas, and to utilize the hydrogen, than just burn only rely on the natural gas. yeah, so yeah, there's not only the utilization, but also a lot of strategy kind of aspect
Any more
for the
questions from the
entire country.
audience? Sorry. The video a bit.
There was a time I was watching a Stanford kind of curriculum or something. Yeah, and I saw a young professor, Professor William Chu. He's in material science, and he was hosting a kind of a seminar, and with his baby, on his shoulder. But luckily, his baby was sleeping on his shoulder. It's not like jumping around. So yeah, so that's what happens when you have to do the seminars or from your home.
19 minutes. Quite because the life is quite difficult. How is the COVID-19 situation over there, and how about the university policy right now? Is it locked down or is no longer locked down over there?
Well, as you know that because our vaccination rate is very high, it's already 83%. So I think from 1 or 2 months ago in July, government from August, government tried to open up and encourage everybody to live a normal life. And our border also is gradually open. So if you are from Germany and from Brunei, fully vaccinated, you can come and travel here. And but that obviously is leading to a drastic increase in the number of cases. So like today, there's a yesterday number, but today the new number is that we have 3,000 more confirmed case, and they are looking at something like 5,000 next week, and so
high actually.
it's quite high. And then the week after, they were also looking at something like 10,000. So that's why from 2 weeks ago, it's less than 2 weeks ago, 1-something weeks ago, the elementary school student, except for 6th grade, everybody, home-based learning. And now also D4 is working from home. And they also, have restrictions for dining out 2-person and for only vaccinated individuals only. Yeah, so it's kind of semi-lockdown, and but the case is keep increasing. Like today in my neighborhood, there is one helper, she get confirmed case, and also in my building there were 2 students confirmed case. So it's like everywhere. This time it's like everywhere. It's very near you.
I see.
So the concern is that because kids, they are not vaccinated. So even though vaccination rate is high, 83%, but the rest are those which cannot be vaccinated. And so a lot of kids also get confirmed case, and so that's the reason for this new restrictions this time. Otherwise, the government is trying to make everybody live more life.
Okay. Thank you very much for all the talk, and very nice meeting you. Okay, so
Thank you.
If there is no more question from the audience, so I think I would like to end the session today. So thank you so much, and hope that we will have the new future collaboration. Okay.
Thank you very much.
Thank you all the audience as well.